So this video is going to be about STP, or spanning tree protocol. We are going to see how it works and why do we need it in the first place. So without any further delay, let's get into it. Let's take a look at this network topology. We have 3 switches connected to end hosts and a switch in the middle connected to the router, and the router is our gateway towards the internet. The reason why this topology is not really a good idea to implement in an actual network is because we have something that is known as a single point of failure. And that point of failure is this cable that is connecting the main switch with the router. If this connection goes down, then all the hosts on this local area network or LAN will lose connectivity. So as a network engineer, when you're implementing network topologies, you must make sure that you have more than a single point of failure, or more than a connection with your gateway. And the reason why we do this is to make sure that we have redundant links. So if one device goes down, in this example, this switch, we would able to connect to the internet regardless. Now, this network topology is far more improved than the previous one. And the reason why I say so is because we don't really have a single point of failure. To demonstrate that, let's take the example of this PC. Let's say this PC is trying to access the internet. It will send this traffic to the switch. If this link is down, in the previous example, the PC or the end host will not be able to access the internet. But since we implemented redundancy in this example, the switch has more than a single interface to forward traffic. And the same applies if this link goes down. Since this gateway will not be able to function anymore, or this router is down, then all the switches will send traffic to this link, and by consequence they will be able to access the internet. But at the same time, when implementing redundancy, we must be careful. And the reason why, because we will be introducing a problem that is known as broadcast storms. And broadcast storms can really destroy a network. To understand what is a broadcast storm, let's take a look at this third topology. Let's say that this PC is trying to send a broadcast message to all the hosts on this network. The way that a switch works is if it receives a broadcast message on a single port, then it will forward that message or flood that message out of all the other ports except the one it received it on. So this switch would receive the broadcast message from this PC, then it will send it on this link and on this link. And the same will happen on the second switch. It will then send it to this link and the other link. But the problem is, when this switch receives the broadcast message, it is going to send it to the neighboring switch also. So the switches will be stuck in a loop. They will keep on sending broadcast messages back and forth to each other. And this is known as a broadcast storm. And this is a big no when it comes to implementing networks, because you are creating congestion and it can even take down the whole network. The way we fix this is by implementing something that is known as STP, or spanning tree protocol. The way STP offers a solution to the problem of broadcast storms is fairly simple. If this PC sends out a broadcast message, then obviously we will create a broadcast storm because of these redundant links. So STP will virtually shut down one of the interfaces in order to prevent these loops from happening. The advantage of having STP is if one of the other links goes down, then the link that we have virtually shut down will go up and take its place. By doing this, we implement redundancy, but at the same time, we prevent loops. One question that may come up in your mind is, how does STP choose which interfaces to stay up and which interfaces must be shut down in order to prevent layer 2 loops from occurring? So in this example, we have something that is known as a priority. As you can see, all switches by default have a priority of 32768. For demonstration reasons, we set the priority on this switch to 28672. The reason why we did this is because STP always chooses the switch with the lowest bridge ID to become the root bridge. What is exactly the root bridge? It is the bridge that has all of its interfaces up and running at all times. So STP will not try to shut any of its interfaces down, but the other switches must shut down the redundant links in order to prevent layer 2 loops from happening. But let's say, for example, all of these switches have the same priority. In this case, STP will default into choosing the bridge or the switch with the lowest MAC address. So this is how STP works. It helps us guarantee reliability and at the same time have redundancy and prevent loops from happening. Thank you for watching, and catch you on the next one.